In this video, I am going to tell about key emerging technologies. There is no significance in the order. I am just telling them in random order. Okay. Let me first start with artificial intelligence, AI. AI refers to the ability of machines or computers to perform tasks that typically require human intelligence, such as visual perception, speech recognition, decision making, and language translation. AI is achieved through the development of algorithms and computer programs that enable machines to learn from data and make decisions based on that data. These algorithms are designed to simulate cognitive functions such as learning, reasoning, and problem solving, and can be used in a wide variety of applications including healthcare, finance, manufacturing, transportation, and entertainment. There are different types of AI, including rule-based systems, machine learning, and deep learning. Rule-based systems use a set of predefined rules to make decisions or take actions, while machine learning algorithms can learn from data without being explicitly programmed. Deep learning is a type of machine learning that uses artificial neural networks to learn from large amounts of data, and it has been particularly successful in applications such as image recognition and natural language processing. AI has the potential to transform many industries and improve people's lives in various ways, but it also raises ethical and social issues such as the potential loss of jobs to automation, privacy concerns, and biases in algorithms. As AI technology continues to evolve and advance, it is important to consider these implications and develop responsible and ethical approaches to its development and use. I have uploaded more than 250 videos related to AI innovations in this YouTube channel. You can watch them by going through the AI playlist. AI is currently being used in a wide range of applications and industries. Let us see some examples. Healthcare. AI is being used to improve patient outcomes by analyzing medical images, identifying disease patterns, and developing personalized treatment plans. For example, AI can analyze medical scans to help detect cancer earlier, or analyze patient data to identify individuals who are at high risk of developing certain diseases. Finance. AI is being used to detect fraudulent transactions, manage portfolios, and develop trading strategies. For example, AI can analyze financial data to identify patterns and trends that humans might miss, and use that information to make more informed investment decisions. Manufacturing. AI is being used to improve efficiency and productivity in factories by automating processes, predicting equipment failures, and optimizing supply chains. For example, AI can analyze data from sensors on machines to predict when maintenance is needed, or use predictive modeling to optimize the production line. Retail. AI is being used to personalize shopping experiences, recommend products, and optimize pricing strategies. For example, AI can analyze customer data to make personalized recommendations, or use predictive modeling to determine the optimal price for a product based on demand. Transportation. AI is being used to improve safety and efficiency in transportation systems, including self-driving cars and drones. For example, AI can analyze sensor data to help cars navigate and avoid accidents, or optimize delivery routes for drones. These are just a few examples of the many ways that AI is currently being used. As the technology continues to evolve, it is likely that we will see even more widespread adoption and integration of AI in various industries and applications. Apart from these current uses of AI, the potential uses of AI in the future are vast and exciting. Let us see some possible scenarios. Autonomous systems. AI will enable autonomous systems such as self-driving cars, drones, and robots to become more prevalent and sophisticated. This will lead to safer and more efficient transportation and manufacturing, and enable new applications in fields such as construction, exploration, and emergency response. Healthcare. AI has the potential to revolutionize healthcare by enabling personalized medicine, faster drug discovery, and remote patient monitoring. AI algorithms could analyze large amounts of data from medical records, imaging, and genomic sequencing to identify patterns and predict disease outcomes. Education. AI could transform education by enabling personalized learning experiences for students, identifying gaps in learning, and providing real-time feedback to teachers. AI could also facilitate more effective training and professional development for educators. Entertainment. AI will enable new forms of entertainment such as virtual reality and augmented reality experiences that are personalized to individual users. AI could also be used to create more realistic and engaging video games and films. Environment. AI will enable more accurate and efficient monitoring and management of natural resources and ecosystems. AI could analyze satellite imagery to predict natural disasters or monitor water quality and air pollution in real time. Next, let us see about 3D printing. 3D printing, also known as additive manufacturing, is a process of creating three-dimensional objects from a digital file by layering materials on top of each other. The process typically involves creating a digital 3D model of the object using computer-aided design (CAD) software, then using a 3D printer to create the physical object. The 3D printing process can use a variety of materials including plastics, metals, ceramics, and even living cells. The type of material used depends on the desired properties of the final object such as strength, flexibility, or conductivity. 3D printing has many potential applications including prototyping. 3D printing is often used to create prototypes of new products, allowing designers to test and refine their designs before going into mass production. Manufacturing. 3D printing can be used for small-scale manufacturing of customized products such as dental implants or hearing aids. It can also be used for on-demand production of replacement parts, reducing the need for large inventories of spare parts. Education. 3D printing can be used in educational settings to teach students about design and engineering and to create physical models of complex concepts that are difficult to visualize. Healthcare. 3D printing can be used to create customized medical implants and prosthetics tailored to the specific needs of individual patients. It can also be used to create models of patient anatomy for surgical planning. Art and design. 3D printing has opened up new possibilities for artists and designers, enabling the creation of complex and intricate sculptures, jewelry, and other objects that would be difficult or impossible to create using traditional manufacturing techniques. Overall, 3D printing has the potential to revolutionize many industries and enable new applications that were previously impossible. As the technology continues to evolve and become more accessible, it is likely that we will see even more innovative uses of 3D printing in the future. I have uploaded many videos about research and innovations related to 3D printing. You can watch them by going through the 3D printing playlist from this channel. Okay. Next, let us see about brain-computer interface. A brain-computer interface (BCI), also known as a brain-machine interface (BMI), is a technology that enables communication between the brain and a computer or other external device. The goal of a BCI is to allow individuals to control devices or communicate without the need for traditional input methods such as a keyboard or mouse. BCIs work by detecting and interpreting brain activity, usually through the use of electroencephalography (EEG) sensors placed on the scalp or directly on the brain. The brain signals are then processed and translated into commands that can be used to control external devices such as prosthetic limbs or computers. BCIs have many potential applications, including medical rehabilitation. BCIs can be used to help individuals with disabilities such as spinal cord injuries or amputations to control prosthetic limbs and regain mobility. Communication. BCIs can be used to enable individuals with communication disabilities such as ALS or cerebral palsy to communicate using a computer or other external device. Gaming and entertainment. BCIs can be used to create more immersive gaming experiences, allowing players to control games using their thoughts or emotions. Education and research. BCIs can be used in educational and research settings to study brain function and to teach students about neuroscience and technology. Military and security. BCAs have potential applications in military and security settings, such as enabling soldiers to control equipment without using their hands. While BCAs have many potential benefits, there are also many ethical and practical considerations that must be addressed, such as ensuring the privacy and security of brain data and addressing the potential risks of brain stimulation. Despite these challenges, BCAs are a rapidly developing field with the potential to revolutionize the way we interact with technology and each other. I have uploaded a lot of videos related to BCA innovations and research. You can watch them by searching BCA from this channel. Next one is nanomedicine. Nanomedicine is a field of medicine that involves the use of nanotechnology, which is the engineering of materials and devices on a nanometer scale to diagnose, treat, and prevent disease. The application of nanotechnology to medicine has the potential to revolutionize healthcare by enabling targeted and personalized therapies, improving drug delivery, and providing new diagnostic tools. Nanomedicine involves the use of nanoparticles, which are particles that are between 1 and 100 nanometers in size. These particles can be engineered to have specific properties, such as the ability to target specific cells or tissues in the body, or to release drugs in a controlled manner. Nanoparticles can be made from a variety of materials, including metals, polymers, and lipids. Nanomedicine has many potential applications, including cancer therapy. Nanoparticles can be designed to specifically target cancer cells, delivering drugs directly to the tumor while minimizing damage to healthy tissue. Diagnostics. Nanoparticles can be used as diagnostic tools, such as in imaging techniques that use nanoparticles to highlight specific tissues or organs. Drug delivery. Nanoparticles can be used to improve drug delivery, allowing drugs to be delivered directly to the site of action in a controlled and sustained manner. Regenerative medicine. Nanoparticles can be used to stimulate tissue regeneration, such as by delivering growth factors or other signaling molecules to damaged tissues. Vaccines. Nanoparticles can be used to improve the efficacy of vaccines by delivering antigens directly to immune cells and stimulating a stronger immune response. Despite the many potential benefits of nanomedicine, there are also potential risks and challenges associated with the use of nanoparticles, such as toxicity and the potential for unintended effects on the body. As such, ongoing research is necessary to ensure the safety and the effectiveness of nanomedicine therapies. Next one, nanosensors. Nanosensors are small-scale devices that can detect and respond to changes in their environment at the nanoscale level. They are used in a wide range of applications, including medicine, environmental monitoring, and electronics. The most common types of nanosensors include those that rely on changes in electrical properties, optical properties, and chemical properties. For example, some nanosensors can detect changes in electrical conductivity when they are exposed to certain chemicals, while others can measure changes in light absorption or fluorescence. One major advantage of nanosensors is their small size, which allows them to be used in very small spaces or even inside living cells. This has led to their use in medical applications, such as detecting cancer cells or monitoring glucose levels in diabetic patients. Another advantage of nanosensors is their high sensitivity, which allows them to detect very small changes in their environment. This makes them useful for monitoring environmental pollutants, detecting pathogens in food, and even detecting explosives. Overall, nanosensors have the potential to revolutionize many industries and improve our ability to detect and respond to changes in our environment. However, there are also concerns about the potential impact of nanosensors on human health and the environment, and more research is needed to fully understand their capabilities and limitations. The next one is self-healing materials. Self-healing materials are a class of materials that have the ability to repair damage or defects that occur over time without the need for human intervention. These materials can be made from a variety of substances, including polymers, metals, ceramics, and composites. There are several ways in which self-healing materials can function. Some materials have the ability to repair themselves through chemical reactions when they come into contact with a particular stimulus, such as heat or light. Others contain microcapsules filled with healing agents that are released when the material is damaged. Still others use networks of fibers or polymers that can reform after being broken. The potential applications of self-healing materials are vast and varied. For example, in automotive industry, self-healing materials could be used to repair scratches and dents on car bodies, reducing the need for costly repairs. In the construction industry, self-healing concrete could be used to repair cracks and other damaged buildings, increasing their lifespan and reducing maintenance costs. In addition to their practical applications, self-healing materials also have the potential to reduce waste and improve sustainability by extending the lifespan of products and reducing the need for replacement materials. While self-healing materials are a promising technology, there are still challenges to overcome before they can be widely adopted. For example, the cost and complexity of producing these materials are currently high, and there is a need for further research to optimize their properties and performance. Next one, quantum dots. Quantum dots are tiny particles made up of semiconductor materials that are only a few nanometers in size. They have unique electronic and optical properties that make them useful in a wide range of applications, including electronics, biomedicine, and energy. The size of a quantum dot is so small that it causes quantum confinement of electrons, which gives them unique optical and electrical properties. Specifically, quantum dots exhibit fluorescence, meaning they can absorb and emit light at specific wavelengths, which can be tuned by changing the size of the particle. This property makes quantum dots useful in applications such as medical imaging and LED displays. Quantum dots are also being explored for use in quantum computing, a type of computing that uses quantum mechanics to perform calculations. Because of their small size and unique electronic properties, quantum dots can be used as qubits, the basic units of quantum computing. Quantum dots are being developed as qubits that can be controlled and manipulated using electric and magnetic fields, making them a promising technology for quantum computing. However, there are also concerns about the potential health and environmental impacts of quantum dots as they contain heavy metals such as cadmium and lead. Research is ongoing to understand these potential risks and to develop safer forms of quantum dots. Overall, quantum dots are a promising area of research with many potential applications. However, more research is needed to optimize their properties, improve their safety, and develop new applications. Next one, carbon nanotubes. Carbon nanotubes are cylindrical structures made up of carbon atoms arranged in a hexagonal lattice. They have unique electronic, mechanical, and thermal properties that make them useful in a wide range of applications, including electronics, material science, and biomedicine. Carbon nanotubes are incredibly strong and stiff with a tensile strength many times that of steel. They are also highly conductive, which makes them useful in electronics and energy storage. Additionally, their small size and high aspect ratio make them useful as reinforcements in composite materials. In biomedicine, carbon nanotubes are being explored for use in drug delivery and tissue engineering due to their ability to penetrate cell membranes and their biocompatibility. However, there are also concerns about the potential toxicity of carbon nanotubes, and research is going to understand and mitigate these risks. Carbon nanotubes have also shown promise in applications such as nanoelectronics, where they are being explored as potential components in smaller, faster, and more efficient devices. Additionally, carbon nanotubes have potential applications in energy storage, where their high surface area and conductivity make them useful in supercapacitors and batteries. Despite their promising properties, there are still challenges to overcome in the development and application of carbon nanotubes. These include improving the scalability and the cost effectiveness of production methods and addressing concerns about their potential toxicity and environmental impact. Nonetheless, carbon nanotubes remain a highly active area of research and development. Next one, metamaterials. Metamaterials are artificially engineered materials that have properties not found in natural materials. They are made up of specially designed structures that manipulate electromagnetic waves, sound waves, and other types of waves in ways that are not possible with natural materials. One of the most common types of metamaterials is known as a negative index material, which has a negative refractive index. This means that it can bend light in the opposite direction of conventional materials. Negative index materials have the potential to create lenses that can focus light to a resolution much smaller than the wavelength of the light, which could have implications for high resolution imaging and communication technologies. Metamaterials can also be designed to exhibit other unusual properties such as perfect absorption, cloaking, and superlensing. Perfection absorption metamaterials can absorb nearly all of the electromagnetic radiation that falls upon them, while cloaking materials can redirect light or other waves around an object, making it invisible. Superlensing metamaterials can go beyond the diffraction limit and provide sub-wavelength resolution. Metamaterials have a wide range of potential applications, including in optics, telecommunications, sensing, and energy. For example, metamaterials could be used to improve the performance of solar cells by manipulating the way light is absorbed and transmitted within the material. They could also be used to create more efficient sensors by enhancing the sensitivity and selectivity of sensing material. Despite their potential, metamaterials are still a relatively new area of research, and there are many challenges to overcome before they can be widely used in practical applications. These challenges include improving the scalability and cost effectiveness of production methods and developing a better understanding of the potential environmental and health impacts of these materials. Nonetheless, the unique properties of metamaterials make them a promising area of research with many potential applications. The next one is microfluidics. Microfluidics is a field of research that deals with the behavior, control, and manipulation of fluids and particles at the microscale level, typically in the range of micrometers to millimeters. Microfluidic devices are characterized by their small size and the ability to precisely control fluid flows and transport, making them useful for a wide range of applications including biomedical analysis, chemical synthesis, and environmental monitoring. Microfluidic devices typically use channels and chambers etched or fabricated on a chip, which can be made from materials such as glass, silicon, or polymers. These channels and chambers can be designed to carry out specific tasks such as mixing and separating fluids, performing chemical reactions, or analyzing biological samples. Microfluidics has the potential to revolutionize a number of fields, including medical diagnostics, drug development, and environmental monitoring, by enabling more precise and efficient manipulation of fluids and particles at a smaller scale than is possible with traditional techniques. Next one, magnetic nanoparticles. Magnetic nanoparticles are a type of nanoparticle that have magnetic properties. They are typically composed of magnetic materials such as iron, cobalt, nickel, or their alloys, and have a size range of about 1 to 100 nanometers. Magnetic nanoparticles have a variety of applications in fields such as biomedicine, environmental monitoring, and data storage. In biomedicine, magnetic nanoparticles can be used for targeted drug delivery, magnetic hyperthermia treatment of cancer, magnetic resonance imaging, MRI, contrast agents, and biosensors. In environmental monitoring, they can be used for water purification and environmental remediation. In data storage, they can be used for high-density magnetic recording. The magnetic properties of these nanoparticles are due to the presence of unpaired electrons in their atomic or molecular orbitals, which create a magnetic moment. The size and shape of the nanoparticles can influence their magnetic properties such as magnetic anisotropy, which can affect their usefulness in different applications. Magnetic nanoparticles can be synthesized using various methods, including chemical precipitation, thermal decomposition, and Sol-Gel synthesis. Surface modification of the nanoparticles with biocompatible materials is often necessary for biomedical applications to prevent aggregation and enhance stability in biological environments. Next one, high temperature superconductivity. High temperature superconductivity, HTS, refers to the phenomenon of materials exhibiting zero electrical resistance at temperatures higher than the boiling point of liquid nitrogen. This is in contrast to traditional superconductors, which typically require temperatures close to absolute zero to exhibit zero electrical resistance. The discovery of high temperature superconductivity in the 1980s sparked great interest in the scientific community due to its potential for practical applications such as more efficient electrical transmission and energy storage. However, the mechanism behind high temperature superconductivity is not yet fully understood, and research in this field is ongoing. The most common types of high temperature superconductors are copper-based compounds known as cuprates and iron-based compounds. These materials have complex crystal structures that contribute to their unique electrical properties. The exact mechanism behind high temperature superconductivity is still a subject of debate, but it is believed to be related to the interactions between the electrons in the material and the lattice vibrations of the crystal structure. Despite the challenges of working with high temperature superconductors, research in this field has continued to advance. Scientists have made progress in developing new materials with even higher superconducting temperatures, as well as understanding the mechanisms behind high temperature superconductivity. Potential applications of high temperature superconductivity include more efficient electrical transmission and energy storage, high-speed transportation systems such as Maglev trains, and powerful electromagnets for scientific research. Next one, lab on a chip. Lab on a chip, LOC, is a miniaturized device that integrates various laboratory functions onto a single microchip. These devices are typically used for chemical or biological analysis, and they enable rapid and precise testing of small sample volumes with high sensitivity and specificity. LOC devices typically consist of channels, chambers, and valves etched or fabricated on a chip using microfabrication techniques. These channels and chambers can be designed to perform specific functions such as mixing, separation, detection, and analysis of samples. The advantages of lab-on-a-chip devices include their small size, low cost, and the ability to automate and streamline laboratory processes. LOC devices have a wide range of applications in fields such as biomedical research, clinical diagnostics, environmental monitoring, and food safety testing. In biomedical research, LOC devices are used for high-throughput screening of drug candidates, cellular analysis, and genomic research. In clinical diagnostics, they are used for point-of-care testing, infectious disease detection, and personalized medicine. In environmental monitoring, they are used for monitoring water quality, air pollution, and soil contamination. In food safety testing, they are used for rapid detection of foodborne pathogens and contaminants. One of the challenges in developing lab-on-a-chip devices is integrating multiple functions onto a single chip without cross-contamination between samples. This requires careful design and optimization of the microfluidic channels and valves, as well as the development of sensitive and specific detection methods. However, advances in microfabrication techniques, nanotechnology, and biosensors continue to drive innovation in this field, making lab-on-a-chip devices increasingly powerful and useful tools for scientific research and practical applications. Next one is graphene. Graphene is a two-dimensional material composed of a single layer of carbon atoms arranged in a hexagonal lattice. It is the basic building block of other carbon-based materials such as graphite, carbon nanotubes, and fluorine. Graphene has attracted considerable attention due to its unique electrical, mechanical, and thermal properties. It is one of the strongest materials known, with a tensile strength more than 100 times greater than steel. It also has high electrical conductivity and mobility, as well as high thermal conductivity. The unique properties of graphene make it attractive for a wide range of applications, including electronics, energy storage, sensors, and biomedical devices. In electronics, graphene can be used to create high-performance transistors, displays, and touchscreens. In energy storage, graphene can be used as an electrode material for batteries and supercapacitors, which could lead to higher energy densities and faster charging times. In sensors, graphene can be used for gas sensing and biosensing applications due to its high surface area and sensitivity to changes in its environment. In biomedical devices, graphene can be used for drug delivery, tissue engineering, and imaging. Graphene can be synthesized using various methods, including mechanical exfoliation, chemical vapor deposition, and solution-based methods. However, the scalability and cost of producing high-quality graphene remain a challenge. Research on graphene continues to expand, with ongoing efforts to better understand its properties, improve its production methods, and develop new applications for this remarkable material. I have uploaded a lot of videos about graphene innovations, research, and news on this YouTube channel. You can find them on a playlist named Graphene. Next one is conductive polymers. Conductive polymers are a class of organic materials that can conduct electricity. They are made up of repeating units of small organic molecules or macromolecules, and their conductivity arises from the movement of charged particles, electrons or ions, through the polymer chain. The electrical conductivity of conductive polymers can be varied over a wide range by adjusting the doping level, which involves the addition or removal of electrons or ions. Doping can be achieved through various means such as chemical oxidation reduction, protonation, deprotonation, or exposure to electromagnetic radiation. Conductive polymers have unique electronic, optical, and mechanical properties that make them attractive for a variety of applications such as electronic devices, sensors, actuators, and energy storage devices. In electronics, conductive polymers can be used for transistors, light-emitting diodes, LEDs, and solar cells. In sensors and actuators, conductive polymers can be used to detect changes in temperature, pressure, humidity, or chemical composition. In energy storage devices, conductive polymers can be used as electrode materials for batteries and supercapacitors. One of the advantages of conductive polymers is their low weight, flexibility, and ease of processing. They can be easily molded or shaped into various forms, including thin films, fibers, and coatings. However, one of the challenges of using conductive polymers is their stability and durability under different conditions. They are often sensitive to environmental factors such as moisture, heat, and light, which can degrade their electrical and mechanical properties. Despite these challenges, research on conductive polymers continues to advance with ongoing efforts to improve their stability, increase their conductivity, and develop new applications for these versatile materials. Next one is bioplastic. Bioplastics are a type of plastic that are made from renewable biomass sources such as vegetable fats and oils, corn starch and pea starch instead of fossil fuels. Bioplastics can be produced using various methods including fermentation, chemical synthesis, and enzymatic catalysis. There are two main types of bioplastics, biodegradable and non-biodegradable. Biodegradable bioplastics can be broken down by natural processes into simpler compounds such as water, carbon dioxide, and biomass. Non-biodegradable bioplastics are made from renewable resources but do not readily decompose in the environment. Bioplastics have a variety of applications in packaging, agriculture, textiles, and biomedical engineering. In packaging, bioplastics can be used for food containers, bags, and disposable cutlery. In agriculture, bioplastics can be used for mulch films and plant parts. In textiles, bioplastics can be used for clothing, shoes, and bags. In biomedical engineering, bioplastics can be used for drug delivery, tissue engineering, and medical implants. One of the advantages of bioplastics is their potential to reduce environmental pollution and greenhouse gas emissions. Bioplastics made from renewable sources can reduce dependence on non-renewable resources and reduce the amount of plastic waste that ends up in landfills or oceans. However, the production of bioplastics requires careful consideration of the environmental impacts of the production process, including the use of land, water, and energy resources, as well as the potential for environmental pollution from the use of fertilizers, pesticides, and other inputs. Next one is aerogel. Aerogel is a synthetic porous material that is composed of a gel in which the liquid component has been replaced with gas, resulting in a solid material that is almost entirely made up of air. Aerogels can be made from various materials, including silica, carbon, and metal oxides, and they are known for their low density, high surface area, and exceptional thermal insulation properties. Aerogels are some of the lightest materials known, with densities ranging from about 0.001 to 0.5 grams per centimeter cube. They also have high surface areas, which can range from 100 to 1000 square meters per gram, making them attractive for applications in catalysis, sensors, and energy storage. Aerogels are also excellent insulators, with thermal conductivities that are typically 1 or 2 orders of magnitude lower than those of other insulating materials. Aerogels have a wide range of applications, including in aerospace, energy, construction, and environmental remediation. In aerospace, aerogels can be used as lightweight insulation for spacecraft and space suits. In energy, aerogels can be used as electrode materials for batteries and supercapacitors, as well as for thermal insulation in buildings and industrial processes. In construction, aerogels can be used as insulation for walls, roofs, and windows. In environmental remediation, aerogels can be used to capture and remove pollutants from air and water. One of the challenges of using aerogels is their brittleness, which can make them difficult to handle and process. However, researchers are developing new methods to produce aerogels that are more flexible and durable, as well as to scale up their production for commercial applications. Overall, aerogels represent a promising class of materials with unique properties that make them attractive for a wide range of applications. Next one is vertical forming. Vertical forming is a method of growing crops in vertically stacked layers or shelves using artificial lighting, controlled temperature and humidity, and precise nutrient delivery systems. The method of forming can be used in both urban and rural settings and is becoming increasingly popular due to its potential to increase crop yield, reduce water usage, and minimize environmental impact. Vertical forming can take many forms, including indoor forms, greenhouses, and shipping container forms. In these systems, crops are grown hydroponically or aeroponically, meaning that they are grown in nutrient-rich water or air without the use of soil. This allows for greater control over plant growth and can lead to faster growth rates and higher yields than traditional forming methods. One of the advantages of vertical forming is its ability to produce fresh produce in urban areas, reducing the distance that food has to travel and minimizing the environmental impact of transportation. Vertical forming can also use significantly less water than traditional forming, as water is recycled and reused in closed-loop systems. Vertical forming also has the potential to be more energy efficient than traditional forming methods, as it can use LED lighting and other technologies to provide precise amounts of light and heat to the crops. Additionally, vertical forming can allow for year-round production, reducing the impact of seasonal variations on crop yield. Despite these advantages, there are also challenges to vertical forming, including the high initial capital cost of setting up a vertical form and the need for skilled workers to operate and maintain the systems. However, as technology continues to improve and the demand for locally grown fresh produce increases, vertical forming is likely to become an increasingly important part of our food system. Next one, cultured meat. Cultured meat, also known as lab-grown meat or cell-based meat, is a type of meat that is produced by growing animal cells in a lab instead of raising and slaughtering animals. Cultured meat is made by taking a small sample of animal cells such as muscle cells and then using biotechnology to replicate those cells and grow them into muscle tissue. Cultured meat has the potential to offer a more sustainable and ethical alternative to traditional meat production. It requires significantly less land, water, and other resources than traditional animal agriculture, and it has the potential to reduce greenhouse gas emissions and other environmental impacts associated with meat production. Additionally, cultured meat does not involve the slaughter of animals, which may be more ethical and appealing to some consumers. There are several challenges to producing cultured meat at scale, including the high cost of production and the need for regulatory approval. However, as technology improves and the demand for sustainable and ethical meat alternatives increases, it is likely that cultured meat will become an increasingly important part of our food system. Cultured meat has the potential to revolutionize the way we produce and consume meat, offering a more sustainable and ethical alternative to traditional animal agriculture. While there are still many challenges to overcome, the growing interest and investment in cultured meat suggests that this technology is likely to play an important role in the future of food production. Next one is Artificial General Intelligence, AGI. Artificial General Intelligence (AGI) refers to the ability of a machine or computer program to perform any intellectual task that a human can do. Unlike narrow AI, which is designed to perform specific tasks such as image recognition or language translation, AGI is capable of learning and adapting to new situations, solving problems, and making decisions in a wide range of contexts. The development of AGI is often seen as the ultimate goal of artificial intelligence research, as it has the potential to fundamentally transform many aspects of our society and economy. An AGI system could be used to solve complex scientific and engineering problems, provide personalized healthcare, manage complex financial systems, and even create new works of art and literature. However, achieving AGI is a challenging and complex problem, It requires the development of machine learning algorithms and hardware that can replicate the complexity and flexibility of the human brain, as well as the ability to integrate and process vast amounts of data from multiple sources. Additionally, there are concerns about the potential risks and ethical implications of AGI. As AGI systems become more intelligent and autonomous, there is a risk that they could become uncontrollable or act in ways that are harmful to humans. To address these concerns, researchers and policymakers are exploring ways to ensure that AGI is developed in a safe and ethical manner with appropriate safeguards and oversight. Overall, while the development of AGI is still in its early stages, it has the potential to be a transformative technology that could shape the future of our society and economy. However, achieving AGI will require significant advances in machine learning, data processing, and hardware development, as well as careful consideration of the ethical and societal implications of this technology. Next one is flexible electronics. Flexible electronics refers to electronic devices and circuits that can be bent, twisted, or stretched without breaking or losing their functionality. Unlike traditional rigid electronics, which are made from materials like silicon that are brittle and inflexible, flexible electronics are made from a range of materials that are designed to be more flexible and durable. Flexible electronics have many potential applications, ranging from wearable health monitors and smart clothing to foldable smartphones and flexible displays. By making electronics more flexible, these devices can be more comfortable and convenient to use, and they can also be made to fit a wide range of body shapes and sizes. There are several challenges to developing flexible electronics, including the need to develop new materials and manufacturing processes that are capable of producing flexible electronic components at scale. Additionally, there is a need to ensure that flexible electronics are reliable and long-lasting, as they may be subjected to more wear and tear than traditional electronics. Despite these challenges, flexible electronics are becoming increasingly common in a variety of applications, from medical devices to consumer electronics. As technology continues to improve, it is likely that flexible electronics will become even more versatile and widely used, transforming the way we interact with electronic devices and opening up new opportunities for innovation and creativity. Next one is Li-Fi. Li-Fi, which stands for light fidelity, is a wireless communication technology that uses light to transmit data. Li-Fi works by modulating the light emitted by LED lamps or other light sources using variations in intensity that are too fast to be detected by the human eye. These variations can be used to transmit data, similar to how radio waves are used in traditional Wi-Fi. One of the main advantages of Li-Fi is its potential for very high-speed data transmission. Because light can be modulated much more quickly than radio waves, Li-Fi has the potential to achieve more faster data transfer rates than traditional Wi-Fi. Additionally, because light does not penetrate walls and other obstacles as easily as radio waves, Li-Fi can be more secure and less susceptible to interference. However, there are also some limitations to Li-Fi. Because it relies on direct line of sight between the transmitter and receiver, it may not be as suitable for certain types of applications or environments, such as large open spaces or outdoor areas. Additionally, because it relies on light sources such as LED lamps, it may not be as widely available or easy to implement as traditional Wi-Fi. Despite these challenges, Li-Fi is an exciting technology with the potential to transform the way we communicate and access information. As the technology continues to evolve and improve, it may become a more common and widely used alternative to traditional Wi-Fi in certain applications and environments. Next one is machine vision. Machine vision, also known as computer vision, is a field of artificial intelligence that focuses on enabling computers to interpret and understand visual information from the world around them. Machine vision uses various techniques and algorithms to analyze digital images and video in order to recognize objects, detect patterns, and extract useful information. Machine vision has a wide range of applications, including industrial automation, surveillance and security, medical imaging, and autonomous vehicles. In manufacturing, for example, machine vision systems can be used to inspect products for defects, measure dimensions and tolerances, and monitor production processes for quality control. In medical imaging, machine vision can be used to identify abnormalities in X-rays or MRI scans, helping doctors to make more accurate diagnosis and treatment decisions. Machine vision systems typically consist of a camera or other imaging device, software algorithms for image processing and analysis, and hardware for data storage and processing. The algorithms used in machine vision may be based on machine learning techniques such as neural networks or decision trees, which can be trained to recognize specific objects or patterns in images. One of the challenges of machine vision is dealing with the complexity and variability of visual data. Real-world images may contain variations in lighting, angle, distance, and other factors that can make object recognition and analysis difficult. To overcome these challenges, machine vision researchers are developing new techniques and algorithms that can handle more complex and varied visual data, as well as hardware that can process and analyze visual data more quickly and efficiently. Next one, Memristors. A Memristor is a two-terminal electronic device that can change its resistance based on the history of the electrical signals that have been applied to it. In other words, it remembers the electrical state it was in the last time it was used. The Memristor was first theorized in 1971 by Leon Chua, a professor of electrical engineering and computer science at the University of California, Berkeley. However, it wasn't until 2008 that the first practical Memristor was developed by a team of researchers at HP Labs. Memristors have several potential applications in electronics, including as a replacement for traditional storage devices such as hard drives and flash memory. Memristors have the potential to be faster, more energy efficient, and more durable than traditional storage devices, and they may also be able to store more data in a smaller physical space. In addition to storage applications, Memristors may also be used in neural networks and other types of artificial intelligence applications. Memristors can be used to model the way that biological neurons work, which could help to develop more efficient and accurate AI systems. Despite their potential advantages, there are still some challenges to developing practical Memristors for widespread use. One of the main challenges is developing manufacturing techniques that can produce Memristors in large quantities and at a reasonable cost. Nonetheless, Memristors are an active area of research and development, and they may play an increasingly important role in the future of electronics and computing. Next one, Neuromorphic computing. Neuromorphic computing is a field of computer engineering that aims to design computer systems that mimic the behavior of the human brain. This type of computing is based on the principles of neuroscience and seeks to create systems that can process and analyze large amounts of data in a way that is more similar to the way the human brain works. One of the key features of neuromorphic computing is the use of artificial neural networks. These networks are composed of interconnected nodes that are modeled after the neurons found in the human brain. Each node or artificial neuron is capable of processing information and communicating with other nodes through a series of electrical signals. Neuromorphic computing also incorporates elements of parallel processing and event-driven computing, which enable the system to process large amounts of data quickly and efficiently. Additionally, neuromorphic systems are designed to be highly adaptable and can learn and evolve over time, similar to the way the human brain can change and adapt based on new experiences. Neuromorphic computing has many potential applications, including in the fields of robotics, image and speech recognition, and natural language processing. For example, neuromorphic systems could be used to create robots that can learn and adapt to their environment, or to develop more advanced systems for analyzing and interpreting medical data. Overall, neuromorphic computing represents a promising area of research that has the potential to revolutionize the way we approach computing and data analysis. Next one, quantum computing. Quantum computing is a field of computing that utilizes the principles of quantum mechanics to perform operations and solve problems that are difficult or impossible for classical computers to handle. Unlike classical computers, which use bits to represent data and perform calculations, quantum computers use quantum bits or qubits, which can exist in multiple states simultaneously. One of the key advantages of quantum computing is its ability to perform calculations at a much faster rate than classical computers. This is because quantum computers can perform many calculations simultaneously, thanks to the principle of superposition, which allows qubits to exist in multiple states at once. Additionally, quantum computers can use a technique called entanglement, which allows multiple qubits to be linked together in such a way that the state of one qubit is dependent on the state of the other. Quantum computing has many potential applications, including in the fields of cryptography, optimization, and machine learning. For example, quantum computers could be used to develop more secure encryption algorithms or to optimize complex logistical problems that would be too difficult for classical computers to handle. However, there are also significant challenges associated with quantum computing. One of the biggest challenges is the issue of quantum decoherence, which occurs when qubits lose their quantum state due to interaction with their environment. Additionally, quantum computers require very specific and controlled environments to operate, which can make them expensive and difficult to build and maintain. Despite these challenges, the field of quantum computing is rapidly advancing, and many researchers and companies are investing in the development of quantum computing technology. As these technologies continue to evolve, they have the potential to fundamentally transform the way we approach computing and problem solving. Next one, Spintronics. Spintronics, also known as spin electronics, is a field of study in electronics and physics that aims to exploit the spin of electrons for use in electronic devices. Unlike conventional electronics, which rely on the charge of electrons to encode information, Spintronics uses the intrinsic spin of electrons to store and manipulate data. In Spintronics, the spin of electrons is used to represent binary information, with upspin electrons representing a 1 and downspin electrons representing a 0. This allows for the creation of non-volatile, low-power memory devices that do not rely on the constant flow of electric current to maintain their state. Spintronics has the potential to revolutionize the electronics industry by enabling the creation of faster, smaller, and more energy-efficient devices. It has already been used in hard disk drives to increase their storage capacity and in magnetic random access memory (MRAM) to create low-power, high-speed memory. Other potential applications of Spintronics include spin-based logic devices, spin-based sensors, and spin-based quantum computers. Spintronics also has implications for the study of fundamental physics, as it allows researchers to study the behavior of spin in materials at the nanoscale. While Spintronics is still a relatively new field, it has already shown great promise and is expected to continue to grow in importance in coming years. Next one, speech recognition. Speech recognition is a technology that enables computers or devices to recognize and interpret spoken language. It uses algorithms and machine learning techniques to convert human speech into digital signals that can be understood by a computer. Speech recognition is used in a wide range of applications, from voice assistants like Siri and Alexa to automated customer service systems, medical transcriptions, and language translation. It is particularly useful for individuals who have difficulty typing, such as those with physical disabilities or those who need to transcribe large amounts of audio. The process of speech recognition involves several steps, including acoustic analysis, feature extraction, acoustic modeling, language modeling, and decoding. During the acoustic analysis stage, the system processes the audio input and extracts features such as pitch, duration, and the intensity. The acoustic model then uses this information to identify phonemes, the basic units of sound in a language. The language model analyzes the sequence of phonemes to determine the most likely word or phrase being spoken, and the decoding stage produces the final output. While speech recognition technology has come a long way in recent years, it still has limitations. Accurately recognizing speech can be challenging in noise environments or when dealing with accents, dialects, or unusual speech patterns. However, ongoing advances in machine learning and natural language processing are helping to improve the accuracy and the effectiveness of speech recognition technology. Next one, Twistronics. Twistronics is a field of study in material science and physics that involves manipulating the twist angle between two layers of two-dimensional materials such as graphene or transition metal dichalcogenides (TMDs). By changing the angle at which these layers are stacked, it is possible to alter the electronic properties of the materials in a precise and controllable way. The term Twistronics was first introduced in a 2018 paper by researchers at the Massachusetts Institute of Technology (MIT), who demonstrated that by adjusting the twist angle between two layers of graphene, they could create a new type of superconductor that exhibits unique electronic properties. One of the key features of Twistronics is that it allows for the creation of what are known as magic angles, where the twist angle between two layers of material is precisely tuned to create new electronic states. These magic angles can give rise to phenomena such as superconductivity, where a material can conduct electricity with zero resistance, or motor insulators, where a material that would normally conduct electricity becomes an insulator. Twistronics has the potential to revolutionize the field of electronics by allowing for the creation of new materials with unique electronic properties that could be used in a variety of applications, such as in ultra-fast electronic devices or in quantum computing. However, there is still much to be learned about the fundamental physics of Twistronics, and research in this field is ongoing. Next, three-dimensional integrated circuit. A three-dimensional integrated circuit, 3D IC, is a type of integrated circuit that involves stacking multiple layers of electronic components, such as transistors and memory cells, on top of one another to create a three-dimensional structure. This approach allows for a greater number of components to be packed into a smaller space, resulting in faster and more efficient circuits. In a traditional two-dimensional IC, the components are arranged side by side on a single plane. However, as the number of components in an IC increases, the size of the chip can become a limiting factor, as the distances between components must be large enough to avoid interference and crosstalk. By stacking components vertically in a 3D IC, the distances between components can be reduced, allowing for faster communication and reduced power consumption. There are several different types of 3D ICs, including through silicon bias TSVs, which are vertical interconnects that allow for communication between different layers of the IC. Another type of 3D IC is the monolithic 3D IC, which involves growing layers of components on top of one another rather than stacking prefabricated components. 3D ICs have several advantages over traditional ICs, including increased speed, reduced power consumption, and reduced form factor. They are particularly well suited for applications such as high performance computing, data centers, and mobile devices. However, there are also some challenges associated with 3D ICs, including increased complexity in design and manufacturing, as well as potential issues with heat dissipation and reliability. Nonetheless, ongoing research in this field is helping to overcome these challenges and improve the performance and efficiency of 3D ICs. The next one, virtual reality, VR, augmented reality, AR. Virtual reality and augmented reality are two related but distinct technologies that have become increasingly popular in recent years. Both involve the use of computer-generated content to create immersive experiences, but they differ in terms of how that content is presented and how users interact with it. Virtual reality is a technology that uses head-mounted displays and other hardware to create a fully immersive digital environment that simulates a real-world experience. The user is typically completely cut off from the real world and is fully immersed in the virtual environment. This technology is often used in gaming, training simulations, and other applications where a highly immersive experience is desired. Augmented reality, AR, on the other hand, involves overlaying digital content onto the real world, typically using a smartphone or other mobile device. This technology allows users to see and interact with virtual objects and information in the real world. AR is often used in applications such as gaming, navigation, and marketing. Both VR and AR have numerous applications across a wide range of industries, including entertainment, education, healthcare, and retail. In education and training, for example, VR and AR can be used to simulate real-world scenarios and provide hands-on experience in a safe and controlled environment. In healthcare, these technologies can be used for surgical training, pain management, and other applications. While VR and AR offer many benefits, there are also some challenges associated with these technologies, including the need for specialized hardware and software, potential issues with motion sickness in VR, and privacy concerns in AR. Nonetheless, ongoing advances in technology and increased adoption of these technologies are helping to address these challenges and make VR and AR more accessible to a wider audience. Mixed reality. MR is a term used to describe a type of technology that combines elements of virtual reality and augmented reality to create a seamless blend of real and digital environments. MR is sometimes also referred to as hybrid reality or extended reality. In MR, digital objects are placed within the real world and users can interact with them in a natural and intuitive way. This is achieved using special hardware such as head-mounted displays and sophisticated software that can track the user's movements and adjust the virtual content accordingly. The result is an immersive experience that combines the best aspects of VR and AR. One of the key advantages of MR is its versatility. Unlike VR, which completely replaces the real world with a digital environment, and AR, which overlays digital content onto the real world, MR can seamlessly blend the two together to create a unique and compelling experience. This opens up a wide range of possibilities for applications across many industries, including gaming, education, healthcare, and more. In gaming, for example, MR can be used to create interactive experiences that blur the lines between the real and virtual worlds, allowing players to fully immerse themselves in the game. In education, MR can be used to create virtual classrooms and interactive learning environments that enhance student engagement and learning outcomes. In healthcare, MR can be used to simulate complex medical procedures and provide hands-on training for medical professionals. While MR is still a relatively new technology, it has already shown great promise in a wide range of applications. As the technology continues to evolve and become more sophisticated, it is likely to become an increasingly important tool for enhancing human experiences in many different contexts. Next one, holography. Holography is a technique used to create three-dimensional images or holograms using lasers. Unlike traditional photographs or images, which are two-dimensional representations of objects or scenes, holograms capture and reproduce the full three-dimensional information of an object or scene. This creates a highly realistic and immersive visual experience that is often compared to the actual object or scene being depicted. The process of creating a hologram involves splitting a laser beam into two parts, a reference beam and an object beam. The object beam is directed onto the object being imaged, and the light scattered by the object is captured on a photographic plate or other light-sensitive medium. The reference beam is also directed onto the photographic plate, and the interference pattern between the two beams is recorded. When the hologram is illuminated with a laser beam, the recorded interference pattern causes the light to diffract, creating a three-dimensional image of the object. Holography has many practical applications in a variety of fields, including art, entertainment, and security. In art, holography is used to create highly realistic and immersive visual experiences that can be used to create stunning visual displays and installations. In entertainment, holography is used to create 3D visual effects for movies, television shows, and live performances. In security, holograms are used to create highly secure and tamper-proof documents and other items such as credit cards and passports. While holography has many practical applications, it is also a fascinating scientific phenomenon that has been studied for many years. In addition to its applications in imaging and display technology, holography has also contributed to our understanding of quantum mechanics and other areas of physics. As technology continues to advance, it is likely that holography will continue to play an important role in many different fields. Next one, optical transistor. An optical transistor is a device that controls the flow of light in much the same way that a conventional electronic transistor controls the flow of electricity. Optical transistors are a key component of many advanced optical systems and devices, including optical communication networks, optical sensors, and optical computing. In an optical transistor, light is used to control the properties of semiconductor material in much the same way that an electrical current is used to control the properties of a conventional transistor. When light is applied to the transistor, it creates a flow of electrons that can be controlled to produce a desired output. This allows the transistor to act as a switch or amplifier for optical signals, much like a conventional transistor does for electrical signals. One of the key advantages of optical transistors is their high speed and bandwidth. Because light travels much faster than electricity, optical transistors can switch and process signals at very high speeds, making them ideal for use in high-speed optical communication networks and other advanced optical systems. Optical transistors are also highly efficient and consume less power than traditional electronic transistors. This makes them ideal for use in low power devices such as sensors and other battery powered devices. While optical transistors are still a relatively new technology, they have already shown great promise in a wide range of applications. As researchers continue to develop new materials and techniques for creating optical transistors, it is likely that these devices will become an increasingly important part of the modern technological landscape, enabling new and innovative optical systems and devices. Next one, artificial photosynthesis. Artificial photosynthesis is a process that mimics the natural process of photosynthesis, which is the process by which plants and other organisms convert sunlight, water, and carbon dioxide into energy-rich organic compounds such as sugars. Artificial photosynthesis aims to create a similar process using man-made materials and techniques in order to produce renewable fuels and other useful chemicals. The basic principle of artificial photosynthesis is to use a catalyst to split water molecules into oxygen and hydrogen. The hydrogen can then be used as a fuel or combined with carbon dioxide to produce hydrocarbons or other chemicals. In order to do this, researchers are exploring a variety of different catalysts such as metal oxides that can absorb sunlight and catalyze the chemical reactions necessary to split water molecules. One of the main advantages of artificial photosynthesis is its potential to provide a renewable and sustainable source of energy. By using sunlight to drive the chemical reactions, artificial photosynthesis can produce fuels and chemicals without relying on fossil fuels, which are a finite resource and contribute to climate change. However, there are still many challenges that must be overcome in order to make artificial photosynthesis a practical and economically viable technology. One of the main challenges is developing efficient and stable catalysts that can effectively split water molecules and produce useful chemicals. Researchers are also exploring ways to integrate artificial photosynthesis into existing energy systems and infrastructure. Despite these challenges, artificial photosynthesis has the potential to play a key role in the transition to a more sustainable and renewable energy future. As research continues, it is likely that this technology will become increasingly important in the years to come. Next one, fusion power. Fusion power is a form of energy that is generated by nuclear fusion, which is the process by which two atomic nuclei come together to form a heavier nucleus, releasing energy in the process. Fusion power has the potential to provide a virtually limitless source of clean and sustainable energy. The basic principle of fusion power is to use the energy released by nuclear fusion to generate heat, which can then be used to produce electricity. To achieve this, researchers are exploring a variety of different methods for achieving controlled nuclear fusion reactions, including magnetic confinement, inertial confinement, and laser-induced fusion. One of the main advantages of fusion power is its potential to provide a virtually unlimited source of energy. Unlike fossil fuels, which are a finite resource that will eventually run out, the fuel for fusion power, typically hydrogen isotopes such as deuterium and tritium, is abundant and readily available. Another advantage of fusion power is that it produces no greenhouse gases or other harmful pollutants. Unlike fossil fuels, which emit large amounts of carbon dioxide and other pollutants when burned, fusion power generates no emissions and produces no radioactive waste. Despite these advantages, there are still many challenges that must be overcome in order to make fusion power a practical and economically viable technology. One of the main challenges is developing efficient and cost-effective fusion reactors that can sustain the necessary temperatures and pressures required for controlled nuclear fusion reactions. Researchers are also exploring ways to minimize the amount of radioactive waste generated by fusion power and to ensure the safety and reliability of fusion reactors. Despite these challenges, fusion power has the potential to play a key role in the transition to a more sustainable and renewable energy future. As research continues, it is likely that this technology will become increasingly important in the years to come. Next one, gravity battery. A gravity battery is a type of energy storage system that uses gravity to store and release energy. It works by raising and lowering heavy objects such as large masses of concrete or steel in order to store or release potential energy. The basic principle of a gravity battery is to raise a heavy object to a high position, such as the top of a tower or building, in order to store potential energy. When energy is needed, the object is allowed to fall or descend, converting the potential energy into kinetic energy, which can then be harnessed and converted into electricity. One of the main advantages of a gravity battery is its ability to store large amounts of energy for long periods of time. Unlike other types of energy storage systems such as batteries or capacitors, which can degrade over time and lose their charge, a gravity battery can store energy indefinitely as long as the heavy object remains in its elevated position. Another advantage of a gravity battery is its scalability. Gravity batteries can be designed to store a wide range of energy capacities, from small-scale systems that can power homes or businesses to large-scale systems that can provide energy to entire cities or regions. Despite these advantages, there are still some challenges that must be overcome in order to make gravity batteries a practical and economically viable technology. One of the main challenges is developing efficient and cost-effective mechanisms for raising and lowering heavy objects such as advanced cranes or hydraulic systems. Researchers are also exploring ways to integrate gravity batteries into existing energy systems and infrastructure. Despite these challenges, gravity batteries have the potential to play a key role in the transition to a more sustainable and renewable energy future. Next, smart grid. A smart grid is an advanced electricity grid that uses digital technologies to monitor and manage the generation, distribution, and consumption of electricity in a more efficient, reliable, and sustainable way. In a traditional electricity grid, electricity is generated at power plants and then transmitted over long distances to homes and businesses through a network of power lines. However, this system is often inefficient, unreliable, and vulnerable to outages and other disruptions. A smart grid, on the other hand, uses digital technologies such as sensors, communication networks, and advanced analytics to enable two-way communication and real-time monitoring of the electricity system. This allows the grid to better anticipate and respond to changes in demand and supply, as well as to more effectively integrate renewable energy sources such as solar and wind power. One of the main benefits of a smart grid is increased energy efficiency. By providing real-time information on electricity usage, a smart grid allows utilities and consumers to better manage and reduce their energy consumption. This can help to lower energy costs, reduce greenhouse gas emissions, and increase energy security. Another benefit of a smart grid is increased reliability and the resiliency. By monitoring the electricity system in real time, a smart grid can detect and respond to disruptions such as power outages more quickly and efficiently. This can help to minimize the impact of these disruptions and improve overall reliability. In addition, a smart grid can help to support the integration of renewable energy sources such as solar and wind power into the electricity system. By providing real-time information on the availability of these energy sources, a smart grid can help utilities to more effectively manage the supply and demand of electricity and to ensure that renewable energy is used as efficiently as possible. Despite these benefits, there are still some challenges that must be overcome in order to fully realize the potential of a smart grid. These challenges include developing new standards and protocols for interoperability and cybersecurity, as well as investing in the necessary infrastructure and technologies. Nonetheless, many countries and regions around the world are already making significant progress in deploying smart grid technologies and realizing the benefits of a more advanced and efficient electricity system. Next one, space-based solar power. Space-based solar power is a proposed technology for generating electricity from the sun using satellites in space. The basic idea is to place large solar panels in orbit around the Earth that can capture the energy of the sun and transmit it back to Earth using microwave or laser beams. The advantage of space-based solar power is that it can capture more of the sun's energy than solar panels on the Earth's surface, since there is no atmosphere or weather to interfere with the sunlight. In addition, space-based solar power can provide a constant source of energy, since the satellites can orbit the Earth and receive sunlight 24 hours a day. The main challenge of space-based solar power is the cost of launching and maintaining the satellites. The solar panels would need to be very large to capture enough energy to make the system viable. and launching and maintaining such large structures in space would be very expensive. There are also concerns about the safety and environmental impact of transmitting energy from space back to Earth using microwave or laser beams. While proponents of space-based solar power argue that the technology can be designed to be safe and environmentally friendly, there are still many unknowns and potential risks that would need to be addressed before the technology could be deployed on a large scale. Despite these challenges, space-based solar power remains an area of active research and development, with several countries and private companies investing in the technology. If the challenges can be overcome, space-based solar power has the potential to provide a significant source of clean, renewable energy that could help to meet the world's growing energy needs while reducing greenhouse gas emissions and mitigating climate change. Next one, artificial uterus. An artificial uterus, also known as an artificial womb, is a hypothetical device that could potentially be used to support the growth and development of a fetus outside of the mother's body. The idea behind an artificial uterus is to provide a safe and controlled environment for fetuses that cannot develop normally in the mother's womb due to various medical conditions or complications. The concept of an artificial uterus has been explored in science fiction for many years, but it is still largely a theoretical idea in the realm of science and medicine. However, there have been some experimental studies using animal models to investigate the feasibility of developing an artificial uterus. The basic idea behind an artificial uterus is to create a sterile artificial environment that mimics the conditions of the mother's womb as closely as possible. The fetus would be placed inside a fluid-filled sac that would be connected to a machine that would supply oxygen, nutrients, and other essential substances to support the fetus's growth and development. The artificial uterus would also need to provide a means for waste removal as well as temperature and pressure regulation to maintain optimal conditions for fetal growth. While the idea of an artificial uterus may sound promising, there are many technical and ethical challenges that would need to be addressed before it could become a viable medical option. For example, there are concerns about the safety and effectiveness of such a device, as well as the potential psychological and emotional effects on both the mother and the child. In addition, there are also ethical considerations related to the use of an artificial uterus, such as questions about the personhood and legal status of fetuses grown outside of a mother's body. Nonetheless, research in this area continues, and it is possible that an artificial uterus may one day become a viable medical option for certain cases where traditional pregnancy is not possible or safe. Next one, neuroprosthetics. Neuroprosthetics is a field of science and engineering that focuses on developing devices or prostheses that can replace or augment the functions of the nervous system. These devices are designed to interface with the nervous system directly, either by electrically stimulating the nerves or by recording signals from the nerves and transmitting them to a computer or other device for processing. The goal of neuroprosthetics is to improve the quality of life for people with neurological disorders or injuries such as spinal cord injuries, Parkinson's disease, or stroke. By providing electrical stimulation or recording and interpreting signals from the nervous system, neuroprosthetic devices can help restore lost or impaired functions such as movement, sensation, or communication. Next one, self-driving car. A self-driving car, also known as an autonomous car, is a vehicle that is capable of sensing its environment and operating without human input. Self-driving cars use a variety of sensors, including cameras, radar, and lidar, to detect their surroundings and make decisions about how to navigate through them. These cars are typically equipped with advanced computer systems and algorithms that enable them to analyze and process the data from their sensors in real time. The development of self-driving cars is driven by the potential benefits they offer, including increased safety, reduced traffic congestion, and improved efficiency. Self-driving cars have the potential to significantly reduce the number of accidents caused by human error, which is currently the leading cause of traffic fatalities. They can also reduce traffic congestion by optimizing the flow of vehicles and reducing the need for parking spaces. Several companies and research institutions are actively working on developing self-driving cars. Some of the major players in the industry include Tesla, Google, Uber, and Apple. However, there are still significant challenges to overcome before self-driving cars can become a mainstream technology. One of the biggest challenges is ensuring that the cars are safe and reliable, particularly in complex and unpredictable environments such as busy urban areas. Regulatory and legal issues are also a significant barrier to the widespread adoption of self-driving cars. Many countries and regions have yet to develop clear regulations and laws around the use of autonomous vehicles, which can create uncertainty and hinder investment in the technology. Despite these challenges, the development of self-driving cars is continuing at a rapid pace, and it is likely that we will see more autonomous vehicles on the roads in the coming years. As the technology matures, self-driving cars have the potential to revolutionize the way we travel and transform the transportation industry. Next, Maglev train. Maglev, short for magnetic levitation, refers to a type of train that is suspended above the tracks using powerful magnets. Unlike conventional trains that run on wheels and tracks, Maglev trains float above the track and are propelled forward by magnetic forces. Maglev trains can reach very high speeds, up to 375 mph, because they do not experience the same friction and resistance as traditional trains. They also produce less noise and vibration and are more energy efficient than conventional trains. Maglev trains are considered to be a very safe mode of transportation, as they do not have any moving parts that can wear out or break. The technology behind Maglev trains has been around for several decades, and several countries have developed and implemented Maglev train systems. The first commercial Maglev train system was built in Shanghai, China in the year 2004 and has since expanded to other cities in China, Japan, and South Korea. Despite their advantages, Maglev trains have some significant limitations. One of the biggest challenges is the high cost of building and maintaining the infrastructure required to support the trains. Maglev tracks require a specialized infrastructure that includes powerful electromagnets, specialized power supplies, and advanced control systems. This can make Maglev train systems very expensive to build and maintain. Another limitation of Maglev trains is their limited range. Maglev trains are typically designed for short to medium distances and are not well suited for long distance travel. This is because the cost of building and maintaining a Maglev train system over a long distance can be prohibitively expensive. Next one, blockchain. Blockchain is a digital ledger technology that allows for secure, decentralized, and transparent record keeping of transactions. A blockchain is essentially a database that is distributed across a network of computers, with each computer storing a copy of the same database. The database consists of a series of blocks, with each block containing a set of transactions. One of the key features of blockchain is that it is designed to be immutable, meaning that once a transaction is recorded in the blockchain, it cannot be altered or deleted. This is achieved through the use of cryptographic techniques that ensure the integrity of the data stored in the blockchain. Blockchain was originally developed as the underlying technology behind the cryptocurrency Bitcoin, but it has since been applied to a wide range of industries and use cases. For example, blockchain can be used for secure online voting, supply chain management, identity verification, and more. One of the main benefits of blockchain is that it eliminates the need for intermediaries such as banks, governments, or other centralized institutions to verify and process transactions. Instead, transactions are verified and processed by the network of computers that make up the blockchain, which makes the process faster, more efficient, and less expensive. Another benefit of blockchain is that it provides a high level of transparency and accountability. Since every transaction is recorded in the blockchain and can be accessed by anyone on the network, it is very difficult to engage in fraudulent or illegal activities without being detected. However, blockchain is not without its challenges. One of the main challenges is scalability, as the current technology is limited in terms of the number of transactions that can be processed at any given time. There are also concerns around the energy consumption of blockchain, as the process of verifying transactions requires significant computing power. Overall, blockchain is a promising technology that has the potential to transform many industries by providing a more secure, transparent, and decentralized way of managing data and transactions. Next one, robotics. Robotics is a field of technology that involves the design, construction, and operation of robots. Robots are machines that are capable of performing a wide range of tasks automatically or with minimal human intervention. They can be programmed to perform a specific task, operate in a specific environment, or interact with humans in a variety of ways. Robotics has applications in many different fields, including manufacturing, healthcare, agriculture, and transportation. In manufacturing, robots are used to automate production processes and perform tasks such as welding, painting, and assembly. In healthcare, robots are used to assist with surgeries, deliver medication, and provide physical therapy. In agriculture, robots are used to plant and harvest crops, while in transportation, robots are used to help with the warehouse logistics and self-driving vehicles. One of the key benefits of robotics is increased efficiency and productivity. Robots can work faster and more accurately than humans, which can lead to increased output and reduced costs. They can also perform tasks that are dangerous, repetitive, or unpleasant for humans, such as working in hazardous environments or performing tedious manual labor. Another benefit of robotics is increased safety. Robots can be designed to work in environments that are dangerous or impossible for humans to access, such as deep sea or outer space. They can also be used to perform tasks that are hazardous for humans, such as working with toxic chemicals or radioactive materials. However, there are also concerns around the impact of robotics on employment. As robots become more advanced and capable, there is a risk that they could replace human workers in many industries, leading to job loss and economic disruption. There are also ethical considerations around the use of robots, such as ensuring that they are safe and do not cause harm to humans. Overall, robotics is a rapidly advancing field that has the potential to transform many industries and improve our quality of life. While there are challenges and concerns around the use of robotics, the benefits of increased efficiency, productivity, and safety cannot be ignored. Next one, CRISPR gene editing. CRISPR, clustered regularly interspaced short palindromic repeats gene editing, is a powerful technique that allows scientists to make precise changes to the DNA of living cells. The CRISPR system is a natural defense mechanism that bacteria use to protect themselves from viral infections. It consists of two components, a guide RNA that can be programmed to target specific sequences of DNA, and an enzyme called a Cas9 that can cut the DNA at the targeted site. Scientists have adopted the CRISPR system for use in gene editing by designing guide RNAs that target specific genes of interest. The Cas9 enzyme then cuts the DNA at the targeted site, allowing researchers to add, delete, or modify specific genes. This has a wide range of potential applications, including in medicine, agriculture, and biotechnology. In medicine, CRISPR gene editing has the potential to revolutionize the treatment of genetic diseases. By correcting or modifying the genes responsible for these diseases, it could be possible to cure or alleviate a wide range of conditions, from cystic fibrosis to sickle cell anemia. CRISPR could also be used to create more effective cancer treatments by modifying the genes of cancer cells to make them more susceptible to existing therapies. In agriculture, CRISPR gene editing could be used to create crops that are more resistant to disease, pests, and environmental stresses. This could help to increase yields and improve food security while reducing the need for harmful pesticides and herbicides. Despite the potential benefits of CRISPR gene editing, there are also ethical and safety concerns. One of the main concerns is the risk of unintended consequences, such as off-target effects or unintended mutations. There is also the possibility that the technology could be used for unethical purposes, such as creating designer babies or enhancing human traits. Overall, CRISPR gene editing is a powerful tool that has the potential to transform many fields, from medicine to agriculture. While there are concerns around its use, ongoing research and regulation will be important in ensuring that it is used ethically and safely. Next one, climate tech. Climate tech refers to a wide range of technologies that are designed to help mitigate or adapt to the impacts of climate change. These technologies can be applied in a variety of fields from energy and transportation to agriculture and building design. The goal of climate tech is to reduce greenhouse gas emissions, improve energy efficiency, and help communities adapt to the impacts of climate change. Some examples of climate tech include renewable energy. Technologies such as solar, wind, hydro, and geothermal power can help reduce the use of fossil fuels and decrease greenhouse gas emissions. Energy storage. Battery and other storage technologies can help to manage the intermittent nature of renewable energy sources, making them more reliable and cost-effective. Carbon capture and storage. These technologies aim to capture carbon dioxide emissions from power plants and industrial processes and store them underground or in other ways. Sustainable agriculture. Technologies such as precision farming, genetic engineering, and vertical farming can help reduce greenhouse gas emissions from agriculture and increase food security. Building design. Green building materials, energy efficient lighting, and smart building systems can help to reduce energy consumption in buildings. Transportation. Electric vehicles, public transportation, and alternative fuels such as hydrogen and biofuels can help to reduce greenhouse gas emissions from transportation. Overall, climate tech is an important area of focus for addressing the global challenge of climate change. It offers the potential for innovative solutions to help reduce emissions and adapt to a changing climate, while also creating new economic opportunities and driving progress towards a more sustainable future. Next one, Perovskite solar cells. Perovskite solar cells are a new type of solar cell that are made from a material called perovskite, which has a unique crystal structure. Perovskite solar cells have been studied since the early 2000s and have rapidly gained attention in the scientific community due to their potential to be a cheaper and more efficient alternative to traditional silicon solar cells. Perovskite solar cells have several advantages over traditional silicon solar cells. They are lightweight, flexible, and can be made using low-cost materials and simple manufacturing processes. Additionally, perovskite solar cells can be engineered to absorb a wider range of the solar spectrum, allowing for higher efficiencies and potentially lower costs. However, there are still several challenges that need to be addressed before perovskite solar cells can be widely adopted. One major challenge is their stability and durability over time, as they are sensitive to moisture and can degrade quickly in the presence of water. Researchers are working on developing strategies to improve the stability and lifespan of the perovskite solar cells. Despite these challenges, perovskite solar cells have already achieved impressive efficiencies in the laboratory, with some devices achieving over 25% efficiency, which is comparable to the best silicon solar cells. This has led to significant interest from the solar industry, with many companies investing in research and development to bring perovskite solar cells to the market. Thanks for watching this video. If you like this video, share it with others. In this YouTube channel, I have uploaded thousands of videos related to emerging technologies. You can go through them to get more ideas about emerging technologies. And I will be uploading latest science and technology news videos here. If you want to watch them, subscribe to this channel. Thanks.